Sine and cosine are actually waves. Yes, they're ratios. Yes, they are ratios. Opposite over hypotenuse and adjacent over hypotenuse. But those ratios, the numbers that sine and cosine go through for given angles, if you guys look, you're labeling a theta axis and a y-axis. Theta is going to be the angles. Y is going to be the ratios. So here are the values of the ratios, and here are the values of the angles for each one. These are called sinusoidal graphs. Sinusoidals. If you say it real fun, you sound like you're from New York or something. Sinusoidals. Maybe from Jersey. Sinusoidals. It's an old movie, but the Disney movie Newsies makes me always think of that one. Sinusoidals. It's called Newsies. It's an old Disney movie. It's a great one. It's also a Broadway play. Sinusoidals. Do they look really similar, sine and cosine? Yeah. You know the crazy thing? If I were to steal this, and let me see if I can steal it, and if I was to put the one on top of the other, oh, screen, don't go asleep, come back. Mrs. Christensen tried to help, but I'm not sure if it's helping. Okay, where's my mouse? Oh, it also clicked buttons when I was, okay, that's cool. Okay, what happens if I take the cosine graph? Don't worry, lots of pieces to it. And what happens if I brought it up? They're so different. Yeah, but are they? They're just shifted. Huh. So they're not actually different. They're really basically the same. I mean, my drawing wasn't perfect, right? It was an approximation. But they're really exactly the same. Just what's different is their phase shift. What's different is where they start. Sine starts in the middle. Sine starts at 0, and then it oscillates up to its maximum, down to its minimum, and it keeps going. Cosine starts maximally displaced, and then it goes ahead and cycles through. There are lots of different characteristics to this graph that we're going to learn. Long story short, I could just give you a nasty equation and be like, hey, for this nasty equation, can you just figure out your horizontal vertical dilations, horizontal vertical shifts, and just go for it? But do you realize this graph is a bit more complicated than any of the parabolas, cubics, absolute value functions, rational functions, exponential functions, ln functions that we've seen this year? It's a little bit harder. And all year, I was like, just get 3 key points down. Just get 3 key points. This one has 5. This one has 5. Because we have equilibrium, or the middle. We have maximum displacement, equilibrium, minimum displacement, and then equilibrium. We have 1, 2, 3, 4, 5 points that make up every cycle. Let me go ahead and highlight for you. And if you have a colored pen or marker, this might be a good time to get it out if you haven't yet already. What sine and cosine's cycles look like. Sine cycle, oh dear. Do you guys mind if I orient the board real fast? It's getting a little bit annoying. Oh, it's going to make music. Back in the day, when we first got the smart boards, there was a smart board trainer person that said basically by dragging you can be more precise as far as landing directly and being able to readjust in the middle of it rather than just like hitting on it and being a little bit off. Does that make sense? Okay, here we go. So now I get my highlighter out. Sine is one cycle from 0 to 2 pi, because then it just starts repeating. Sine's one cycle like this. Whereas cosine's one cycle looks like this. And as you guys saw a second ago, they really are super similar. They're both waves. They both oscillate. Wait a minute. We know that. Unit circle. They both have the exact same numbers, just at different places. They both have the exact same number, just at different places. So cosine's cycle and sine's cycle, if I was to shift one, it would basically run into the other. However, as we just talked about, there can be transformations. Some different key vocab words that you're going to listen to, and actually you probably have already seen. Frequency, period, amplitude. phase shift, sinusoidal axis. Ooh, that one's good. So let's go ahead and get into it. Key points, as I've already said, sine has this shape starting in the middle and going up, down, down further. Middle, up, middle, bottom, middle. Cosine, top, middle, bottom, middle, top. Each of them have a particular shape to their cycle. Cyclic is a way of describing these waves. They move in cycles. Ooh, cycles. What else move in cycles? The tides? Anyway. Tides, waves, cycles. Moon? Anyway. Now we're getting random, but maybe not. Each of these sinusoidal waves or sinusoidal curves, we could call them, have key points, except instead of the 2 or the 3 that we needed for lines and parabolas and exponentials and logarithms, we need 5. 5 per cycle, sectioning the curve into quarter cycles. You have 5 fingers, yeah? How many spaces in between those fingers? Your 5 fingers cut the space from beginning to end into 4 sections, 1 and 2 and 3 and 4, yeah? 5 fingers, 4 sections. So quarter cycles is because that's what, with those 5 points, how my curves have been sectioned off. 1 and 2 and 3 and 4. 1 and 2 and 3 and 4. If we find a fourth of the period, we are able to figure out what one cycle, or what the distance is of one cycle. So a fourth of the period is one cycle. I apologize. A fourth of the period is a fourth of a cycle. And those cycles, those quarter cycles. Now here's elaborate, but somewhat just a trick. If the transformation is fairly basic, we might not have to go through this whole elaborate setup that I'm going to show you as far as how to graph any sinusoidal curve that has been transformed in any way, shape, or form. Because for instance, if you guys look at this function, what could you tell me about sine? How did it change? Parent function, sine of x. If you multiply by 2 on the outside, what just happened? Vertical stretch by a factor of, it's on the outside, it's multiplied. Stretch by a factor of 2. Yeah, that's what's going on with this guy. 2 sine of x. So wait, did the horizontals change at all? Just the verticals, which means when sine of 0 was 0 a second ago, that's still true. And when sine of pi was 0 a second ago, that's still true. Uh-oh, I need to go to 4 pi, though. Struggle, 1 pi, 2 pi, 3 pi, 4 pi. But a second ago, guys, look at your graph. Wasn't sine at 0 at pi? Wasn't sine at 0 at 2 pi? What do you think is going to happen at 3 pi and 4 pi? Sine's also going to be 0. What's going to happen at negative pi? Sine's also going to be at 0. Every pi hits. And we've seen that in the original graph. Sine hits 0 every pi, which corresponds to the unit circle. Also, y is 0 at every pi. But what's important, vertical stretch by 2, what was happening at pi over 2 and 3 pi over 2? Well, first of all, what was happening at pi over 2? Sine went from 0 to 1. But why am I going to change that and now go up to 2? Vertical stretch. And then at 3 pi over 2, where was sine? Negative. Oh, look at your original graph. Didn't it go down to negative 1? So where's it going to go down to? Negative 2. And then what happens as soon as you get back to 2 pi? There was no horizontal change. Well, guys, when we go around the unit circle to 2 pi, doesn't it just start hitting the same angles again? Oh, so isn't it just going to go back up to 2 at whatever that half pi is, which would be 5 pi over 2, and then at the next pi over 2, it's going to go down again? Yeah. And 4 pi, it comes back up. Now, technically, this says stop at 4 pi. Okay, fine, stop. Stop at pi. Well, if I go backwards, Wait, if I go backwards. In the unit circle, if I go backwards, am I in the first quadrant or am I in the fourth quadrant? Okay, so I'm not going to copy the first quadrant. Copy this guy. Oh. There we go.
Don't you just start with negative pi?
You could. You could. I usually start at 0. I don't know why. In my head, sine of 0 is 0. It's kind of easier. But yeah, you could have started at negative pi. So guys, if there's just a vertical stretch by 2, no big dealio. You can use your exact same x's on the x-axis, and you can just say, sweet, instead of going to 1, I'm going to 2. Instead of going to negative 1, I'm going to negative 2. We don't necessarily need to figure out everybody in between because they're nasty. They're 1/2 multiplied by 2, and root 3 over 2's multiplied by 2, and root 2 over 2's multiplied by 2. Ew! But 1 multiplied by 2, that's easy. Negative 1 multiplied by 2, that's easy. But that was easy. As far as only one transformation, and it was just a vertical stretch. Whew. Question, what would change if I was to give you, I can dual page in case you're still doing it. What would change if I was to ask you instead to sketch y equals cosine of 1/4 x? Still only one change. Horizontal, yes. Shrink, no. Horizontal stretch. Remember, inside is reciprocal of what I think. Different than what I think. Horizontal stretch by what? If I multiply the x's by 1/4, don't they? I need to multiply the x's by a factor of 4. Horizontal stretch by 4. That's kind of review with parent functions, just it's new when we have sine curve. Oh, cosine curve. So this is a little different. And this one, when I go to graph, am I changing the going up to 1 and going down to negative 1 part? Nope, because there's no vertical change. But what I am changing, if I was still doing the exact same, guys, look at your cosine curve. Can I still say that cosine of 0 is 1? Well, wait. Plugging in 0, this doesn't change 0, does it? Cosine of 0 is still cosine of 0. Or think about it. If I multiply 0 by 4, does that change anything? 0 by 4? No. 0 is the same. But here's the problem. Am I still just going to go to 2 pi and finish? How long is it going to take for me to finish now? Why 4 pi? Oh. It's not even going to work, is it? Well, hopefully this wouldn't be my interval that I just made up. Hopefully they would say to go to 8 pi. If not, I'd have some issues. Because why did Kyle say, no, go to 8 pi? What am I supposed to do if I have a horizontal stretch? Multiply the x's by? Yeah, the factor, right? So what's the factor? 4. How long did it take cosine to finish in the olden days, aka like the top of the notes? 2 pi. But how long now? Well, struggle. So if cosine used to hit the middle or the axis, used to hit 0 at pi over 2, well, that times 4 now 2 pi. Oh, stink. So pi over 2 got 4, that's 2 pi. Then cosine used to hit negative 1 at pi, well, that times 4 is 4 pi. Cosine used to hit back up to 0 at 3 pi over 2 times 4 ends up. I knew it because it used to 2 pi and it had to be 4 times. It was without having to point. I have thought 8 pi was this distance cut into fourths. What's 8 pi fourths? Pi's. What? Oh! From one key point to the next 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 key point. We go 2 pi, 2 pi, 2 pi, 2 pi. And now, now I'm going to need to go backwards. Struggle is I can't go all the way there, so it's going to be something like that. I stretch it by a factor of 4. could I have taken each and every 1, 0, sorry. Yeah, 1, 0, pi over 2, 0, 1, my bad. 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and back to 2 pi, 1. I could have taken each of those and multiplied x's by 4. That totally works. But maybe it's easier to say, hey, the whole thing is going to be 8 pi, 4 times as long. Cut it into fourths. Ha-ha! By 2's, by 2's, by 2's. Zoop, zoop, zoop. There's my wave. That's kind of the idea of what I'm going to show you and what we're going to develop a little bit more tomorrow, which is why this homework isn't due until Friday. Because there's a lot of different transformations that can happen, and some of them get really, really tricky if we have to do all these different movements and changes and multiplying and adding to all these points. It's going to be a lot easier. It's going to be a lot easier if I give you some tricks. So there are technically 2 different ways this can appear. Let me go ahead and zoom in on it. It's basically tricks to graphing transformed sinusoids. It's basically tricks to graphing, shortcuts to graphing transformed sinusoids. These equations can show up 2 different ways, but long story short, at the end of the day, based on the transformations that we know, this D is going to move our sinusoidal axis, aka the middle of my wave at y equals d. All the waves we've seen so far is on the x-axis at y equals 0, but that could shift up or down. That could shift up or down. A is going to be, if you guys know anything about waves, maybe you know there's something called an amplitude. Amplitude is how high, how low. When your music's turned up loud, the sound waves are going to be pretty stinking high and low. When your music's soft, there's not near as much variance. Amplitude, amp it up. Oh, is that a thing? Amplitude, how high, how low. From the middle. Oh, and the middle is the sinusoidal axis. Exactly. How high, how low from the middle. The middle is the sinusoidal axis. Exactly. We have 2 other ones we're going to look at tomorrow and put it all together and see, is there an easier way to graph these guys without having to take 5 points and change them all with the transformations? All right, cool kids? If I were you, catch up on other stuff tonight because tomorrow's going to be a pretty big math night. Bye, guys.